Okay, so yesterday we were introduced to the rational root theorem. Now we're going to use the rational root theorem to actually find all the roots to these polynomial equations. But before we do that, let's do this little warm-up. This is similar to the questions you had on the homework from the day before. So you might find it helpful to go back and redo that assignment. The assignment still is open. So you can go back and redo it. It'll be a good review. So it says select all the roots below that cannot be roots of the given equation. Well, these are all rational, so we can use the rational root theorem. That means we can write in the form P over Q. What's true about P? It has to be factors of your what? Your constant term, which is negative 15 on this equation. And then the bottom, the denominator, has to be factors of your leading coefficient. And on this equation, my leading coefficient is 2. So let's look at the first one. We get 7 over 2. Is 7 a factor of negative 15? No, it's not. So it cannot be a rational root according to the rational root theorem, because 7 doesn't divide 15. What about the next one? Negative 5 over 4. Does negative 5 go into 15? Yes. So the numerator is okay. What about the denominator? Does 4 go into 2? Is 4 a factor of 2? No, it's not. So this cannot be a rational root for that equation. What about the next one? C, negative 1/2. Is negative 1 a factor of 15? Yep. Is 2 a factor of 2? Yes. So this is, okay, this could be a possible rational root. And then D, what about 2/3? Is 2 a factor of 15? Nope. So it's asking us to find the ones that cannot be roots of the given equation. So the answers would be choice A, B, and D. Only C might be. We don't know if it is or not, but we could find out if it is by using synthetic division, but it didn't ask that. It asked what roots cannot be roots of the given equation. Negative 1/2 has a possibility to be a root of it. But these other three do not. All right, so here's an example. We started this on yesterday's lesson. We listed out all the list of possible rational roots. Well, today I want to solve it. It says use the remainder root theorem to find all the roots of the given polynomial equation. So you're going to start all of these off the same way. I want to always see this step. So always do this step. Show me this step. Always. So we're going to have our P over Q. So P is going to be factors of negative 1. Q is going to be factors of my leading coefficient, which is 2. So let's list out all the factors of negative 1. So we got 1 and negative 1. Let's list out all the factors of 2. Well, 1 and 2 are all the factors of 2, right? But you also have 1 and negative 1, positive and negative 2. So if we have a rational root, if this equation has a rational root, it has to be in this form. So what we want to do is we want to generate this list. I want to see this list every time. Just label it PRR. Make sure I can see that list. So you're going to take your numerator, which is 1, and you're going to put it over your first denominator. 1 over 1 reduces down to 1. So one possible rational root could be positive 1 or negative 1. Now I'm going to do the same thing, but this time, instead of putting it 1 over 1, I'm going to put 1 over 2 and see if I get a new group of numbers. What's 1 over 2 reduce down to? 1/2. All right, so these problems are really long. So you're not going to have a lot of these on today's assignment. So what we need to do now is test these rational roots, these possible rational roots. We're trying to find one that works. I only need to find one that works. I'll just tell you why here in a minute. So you don't know which one's going to work. You have no clue. I always start on the right and just go left. So I'm just going to test one first. And hopefully we get lucky and one is the one that works. So we're going to use synthetic division to test these. So let's make sure none of the variables are skipped over. We got x to the third, x to the second, x to the first, x to the 0. So we have all of our variables. None are skipped over. So we don't have to use any placeholder values. So let's list out the coefficients. 2, -1, 2, and -1. Now, let's see if this is going to work here. So is 1 a root of this? How do I know if 1's a root? If I get a remainder of 0 when I use synthetic division. So I'll drop the 2 down under the line. I write 2 down there. Then I take 1 times 2. 1 times 2 is 2. And then I'm going to take -1 plus 2, which is 1. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. -1 plus 3 is 2. The remainder is not 0. So that means 1 is not a root of it. So now let's see if -1 is a root. So let's try -1 out. Is -1 a root? So you're just going to do the process all over again. Again, you have no clue which one's going to work. That's why this is a long process. That's why I'm not going to be giving you a bunch of these problems. So bring the 2 under the line, multiply by your number in your box. -1 times 2 is -2. Write that up here. Add these together. -1 plus -2 is -3. -1 times -3 is +3. 2 plus 3 is 5. -1 times 5 is -5. We get -6. So I'm not getting too lucky here. We eliminated 2 of them. Remember, we're only going to find one of them that works. So it has to be either 1/2 or -1/2. All right, so let's try 1/2. So let's put 1/2 in the box and see what happens. Again, we just list out the coefficients. Drop the 2 down. We got 2. 1/2 times 2. 1/2 times 2 is 1. -1 plus 1 is 0. 1/2 times 0 is 0. 2 plus 0 is 2. 1/2 times 2 is 1. And guess what? We finally found one that works. The remainder is 0. Okay? So we found one of the roots. But it's asking you to find all of the roots. It says find all the roots. Well, what type of equation is this? It's a cubic equation. That means it has degree 3. That means it has 3 roots. We got one of them. One of the roots is 1/2. Okay? It still has 2 more. All right, so here's how you can find the other 2. It's kind of like synthetic division and long division. Remember, we started with an equation to the 3rd power. So what we have here is an equation to the 2nd power now. I can rewrite this as it's always 1 degree less. We had degree 3, so this is going to be 2x squared plus 0x plus 2 is equal to 0. I'm going to solve this equation here. Well, what is 0x? That's just 0, right? So I can simplify this down further. So we got 2x squared plus 2 is equal to 0. What do we have here? We have a quadratic equation. We know how to solve quadratic equations. Okay? So we got to decide what method is going to be the best way to solve this. Well, we only have an x squared term. So we're going to use the square root method. So what we're going to do is we're going to subtract 2 from both sides. These cancel out. We get 2x squared is equal to negative 2. Divide by 2, divide by 2. We get x squared is equal to negative 1. It's called the square root method that we're using. The last step is to take the square root of both sides. Just remember, whenever you use the square root method, you got to put plus and minus on your final answer. So x is equal to plus or minus the square root of negative 1. But what is the square root of negative 1? That's I. That's what we define the imaginary number as. So here are our last two roots. So the roots are 1/2 I and negative I. These are 3 roots. All right, I want to look at one more problem here. Okay, example 3. It says generate a list of possible rational roots for the following polynomial equation. Do not solve it. So you're not actually solving it. I just want you to generate that list. Okay? I want to see that you can make that list. It's very important. That's the most important step. If you can't do that, you're not going to be able to do the rest of the problem. So I want to see this. So let's do our P over Q. So our P is going to be factors of what? Factors of negative 21 over factors of our leading coefficient, which is 6. So let's list out all the factors of 21. So we got 1 times 21, right? 2 doesn't go in 21. We got 3 and 7. Are there any other factors of 21? No. So it's 1, 3, and 7. But we could have positive and negative 1, positive and negative 3, positive and negative 7, positive and negative 21. And then let's do the bottom. So on the bottom, we want factors of 6. So we got 1 and 6, 2 and 3, and that's it. And then of course we got our positive and negatives. So here's what I want you to do. I want you to generate that list. I always want to see this. Label it again, PRR, which stands for list of possible rational roots. So here's what we're going to do. We're going to take our first number on top, which is 1. All right? Actually, let's just take all these numbers on top. 1, 3, 7, and 21. Let's take all of those numbers and put them over our first number in the denominator. So if we put 1 over 1, that reduces down to 1. 3 over 1 is 3. 7 over 1 is 7. 21 over 1 is 21. So if I take each of my numbers in my numerator and put them over 1, I end up with positive and negative 1, positive negative 3, positive negative 7, positive negative 21. Now what I want to do is I want to take each of those numbers from the top, this time write them over 2, and see if I get any new numbers. So let's put each of these over 2 and see what we end up with. All right, so we're going to put 1 over 2. What's 1 over 2? 1/2, right? So that's a new number. We don't have that on our list, so let's add it. 3 over 2. It's not on my list, so add it to your list. 7 over 2. It's not on my list, so let's add it to our list. And then 21 over 2. It's not on our list. All right, so this time we're going to take all the 2 numbers on top and this time put them over 3. Let's see if we're getting new ones. All right, so 1 over 3 is 1/3. That's not on our list. 3 over 3 reduces down to 1. We already have that on our list. We already have 1 on our list. So when you put 3 over 3, this reduces down to 1. 7 over 3 is not on there. So that's going to be on my list. And then last, let's do 21 over 3. What's 21 over 3? 7. I already have 7 on the list. So Last thing we're gonna do now is put all the numbers on top over 6 and see if we get any new ones generated. So we're gonna have 1 over 6. 1 over 6 is 1/6. That's a new one. 3 over 6. 3 over 6 is 1/2. Not a new. We already have 1/2. 7 over 6. Do I have 7 over 6? Nope. That's another one. And then last, what's 21 over 6? Well, we divide those both by what? 3? That's 7/2. Do we have 7/2 already? Yep. So this is our list. Right here, it's a really large list. That's why I wanted to do this one. With all the ones we've done up to this point, they're pretty short. Now, if we were trying to solve this one, we would have to find one of these that works. There's a lot to choose from. We don't know which one works. Okay? But it says don't solve it. All right? So again, I want to see this every time, even on the ones that you're solving. I want to see this list. I want to see that list of possible rational roots. So be sure to show that.